Okay. Yep. So I think almost everyone is connected by now. So once again, welcome to the webinar. My name is Katarina. I'm from the Adbian team, and I will guide you through today's webinar. The webinar will be focusing on mastering tree risk assessments and on advanced biomechanics and some modern tools in this world. Today, we'll have three different presentations with three different speakers. The first one is JP McDonnell from SavATree, joining us from Tennessee today. The second one will be Ondrej Kolarik, who is the founder of Adbian from the Czech Republic. And then the last one is Simon Stratford of Stratford Trees, joining us from Montana today. If you have any questions on the way during the presentations, there is a Q&A section, so feel free to type your questions in there. And in the end, we'll definitely have some time to look at those questions, answer them, and maybe have some discussion about them. The session is recorded, so there will be a recording and we will share it with you afterwards. And lastly, a very important thing that those of you who want to get the SACU credits afterwards, please make sure that you shared your certification number with us or get in touch with us after the webinar, so we'll make sure you get the credits afterwards. So before we will move to the first presentation, I would like to share some exciting news from Adbian. So Adbian is originally a company from the Czech Republic in Europe, but the most recent and very exciting news is that the part of our team actually relocated to the USA, to Brooklyn, New York City 3 weeks ago. You can meet us in these upcoming events and conferences. You'll see that we'll be traveling the States quite a bit in the upcoming weeks and months. So, for example, next week we'll be at the Relief Annual Conference in Oswego. Then by the end of the month, we are going to the Urban Forestry Summit in Florida. And then September is going to be quite intense, where you'll find us in the Trees and Utilities event in Tennessee, on Trees and Technology Day near Atlanta, and lastly on the Texas Tree Conference in Waco in Texas. And then we are very excited to share that we'll be actually speaking on the ISA Annual International Conference in New Zealand in October. So definitely, if you are heading to one of those, stop by. We'll be very happy to meet you in person. And lastly, some technical update. We just want to share that we are always trying to improve our services. And recently we were working on in some improvements in the app interface to make the whole process and navigation in the app smoother and more user-friendly. All right, so that would be all from my side for the beginning. And now I would like to welcome the first speaker, JP McDonnell, who is the Consulting Group Assistant Manager from SavATree. JP is in his field and in the consultancy field for more than 10 years, and he focuses on tree assessments and tree preservations and some others. JP, the word is yours. Feel free to share your presentation and you can go ahead.
Thank you very much, Katarina. Let's see if I can get situated here. So I know we've got a pretty diverse international audience here. So as typical of an American, I want to discuss what we do here in the US. So I'll be starting us off with an overview of tree risk assessment from the International Society of Arboriculture's Best Management Practice approach and the American National Standards Institute A300, and describing some common as well as emerging advanced techniques. So for those of you who are tree risk assessment qualified, parts of my presentation will be review, but I wanted to provide an overview of the ISA Best Management Practice approach for those not familiar with it. So in any risk assessment context, risk is defined as the probability of an event occurring times the consequences if that event were to occur. And globally, there are several different methodologies used by arborists to systematically identify, analyze, and communicate tree risk. There's qualitative and quantitative approaches, and it's important to note that we assess the risk of structural failures associated with trees. However, there are still conflicts that can pose risk to people or property that are not considered during a tree risk assessment. Some examples of these conflicts include root damage to infrastructure, obstructions in the right-of-way, blocked signs, or trip hazards. As mentioned, I'll be focusing on the ISA BMP approach, which is a qualitative matrix-based approach. This relies on descriptive terminology, as you can see in these matrices, rather than numbers. And this approach relies on these two matrices, the likelihood matrix on the left and the risk rating matrix on the right. The first matrix allows the arborist to categorize the likelihood of tree or tree part failure and the likelihood of impacting a specified target. And then you move on to the risk rating matrix on the right, which introduces the consequences of failure. So for those not as familiar with tree risk assessment, in the United States, the International Society of Arboriculture educates and trains arborists on tree risk assessment via the Tree Risk Assessment Qualification Program, or TRAQ. And this is a 2.5 day training program with a field exam and a written or a multiple choice paper exam. And TRAQ qualified arborists are required to renew every 5 years, and a change coming up is renewal every 7 years rather than 5 years. In the United States, the American National Standards Institute A300 tree care standard is the industry consensus standard for tree care operations. This standard was recently consolidated and includes 10 clauses, or 10 different sections, each related to a different tree care operation, and tree risk assessment is one of these clauses. This document sets the standard for care for arborists, sets the standard of care for arborists in the US. And for those not as familiar with the United States, we have a pretty litigious society, which makes following industry standards very important. On the right, you see the ISA BMP for tree risk assessment. The ISA develops companion publications to the A300 standard, and this provides more detail, explanations, and guidelines to arborists to help them interpret the standard. And it is a little surprising how so many arborists still confuse these two, because they are separate publications and they are both important to know. Another update this year, the third edition of the Tree Risk Assessment BMP was released, and this includes more detail to help reduce variability between tree risk assessors. It includes important guidance on the difference between a tree inspection, a tree risk assessment, and a worksite inspection. And there's new figures and diagrams. I briefly wanted to touch on the ANSI A300 flowchart here, which gives a high-level look at the process for completing a risk assessment. So you always start with the why, or the objective for performing any tree care operation, including tree risk assessment. You then develop your specifications, so you ensure that your scope of work is clear and agreed upon with the tree manager. Then you'd conduct your assessment based on that scope of work, collect relevant data, analyze and categorize risk, and develop risk mitigation options or recommendations. You then report your findings and risk mitigation options to the tree manager. Per ANSI A300, there are 3 levels of risk assessment. The first level is a limited visual risk assessment from a specified perspective. The most common level is the level 2 basic tree risk assessment, which is a 360-degree ground-based visual. And then level 3 advanced risk assessment, is anything using any technology or technique over and above what is required in a level 2 basic assessment. So we'll go through these levels briefly here. So visual assessment can be from a walk by, a drive by, could be an aerial patrol via drone, or it could even be from remote sensing or imaging. And this, of course, is the fastest and least thorough risk assessment, and typically is performed on a large number of trees to identify those trees with open or obvious defects for further inspection. Here's a diagram of an example of what a limited visual might look like. So this arborist here would be walking along this trail, looking at these trees that could fail on this trail and potentially impact a person, and looking for open and obvious defects. If they saw one, then they would probably call that tree out for a higher level inspection, such as a level 2 basic assessment. Onto the basic assessment. As mentioned, this is a 360-degree ground-based visual of above ground tree parts, including visible roots, trunk, and crown. We look at targets and the surrounding site. This is the most common tree risk assessment performed here in the United States. Of course, includes a risk rating, mitigation options and recommendations, and a residual risk rating for those mitigation options. Here's an example. So you have a scope of work before you get on site. It was agreed that we would perform a basic level 2 tree risk assessment on this oak tree. I come to the site, look at potential targets. So I see a bench, picnic table, sidewalk there. So pedestrians would be the target here. Then you'd walk up to the tree. I usually go from the ground up. So I walk around this tree looking for significant defects, which this tree obviously got struck by lightning. I use a mallet and a probe typically. Those are optional, simple tools, but can provide you with a little bit more information. After identifying the significant defects, you categorize the likelihood of failure, the likelihood of impacting those targets, and the consequences, and get your risk rating and report this to the tree risk manager. On to level 3, advanced assessments. These use a technique or tool over and above what is required for a basic assessment, generally takes longer and is therefore more expensive than a basic risk assessment, but of course can provide additional information that the tree manager would not have had without conducting this advanced assessment. Brief look at conditions of concerns or defects that a risk assessor is looking for: dead or dying tree parts, weakly attached branches or codominant stems. So we had a limb failure on the left from weak branch unions. We've got codominant limbs in the middle with potentially included bark, and on the right, multiple scaffold limbs originating from the same height of the tree. Broken or hanging branches, cracks, ribs, or seams. Looking for root problems such as girdling roots on the left, root damage in the middle, or root decay, which can be identified by fruiting bodies as a positive indicator. Missing or decayed wood on the left, we've got a small cavity with some response growth, but we don't know how much decay is inside there. In the middle, we've got an open cavity with quite a bit of response growth around the edges there. And on the right, fruiting bodies, positive indicator of decay. You typically mallet or sound that trunk to get an idea of how much decay might be in there if you can't see it. Poor tree architecture is another potential condition of concern. On the left, we've got lion's-tailed scaffold limb. In the middle, we've got a large limb on the right there, which is almost the same size as the trunk, which can be an indicator of potential higher likelihood of failure. And on the right, we've got an asymmetrical crown, pretty obscene pruning job there. Here in the middle, we've got low live crown ratio of pine trees, which can potentially be an indicator of higher likelihood of failure. On the left, we've got a lean. Now on to advanced tree risk assessment techniques. As you can see, there's a long list of techniques and tools that an arborist can use to perform an advanced risk assessment. Some situations might call for multiple techniques to be performed as part of one assessment. I'm not going to go through all of these, but I'm going to go through a handful which are common or are emerging techniques. A detailed target analysis can be conducted to gather more information about likelihood of impact of targets or potentially consequences. So a target zone can be overlaid over aerial imagery based on tree height. Research on property values could be obtained to more accurately categorize consequences of failure, or use and occupancy statistics can be measured. So you determine where and how often people or other targets are in that target zone. Assessments are fairly common here, can be conducted from the crown via climbing, performed from a ladder, or from an aerial lift. Aerial assessments often do include decay testing as well, and aerial assessments typically include taking photographs and potentially measurements of specified conditions like decay in the crown. On the left, we've got a climber using a resistance drill. In the middle, there's a climber probing and taking photographs of a cavity, and on the right, another climber using a resistance drill. It's an example of another photograph of a defect taken by a climber as part of an advanced assessment. Drones are becoming more common these days in arboriculture. They can be used to perform a limited visual level 1 or a level 3 advanced assessment. So it's important to note the difference there and be aware of whether you're performing a level 1 or a level 3. So generally, when assessing populations of trees using a drone, that would be considered a level 1 limited visual assessment, and you'd be looking for trees that might need further assessment via basic level 2 or potentially advanced assessment. Typically, when you're assessing an individual tree using a drone to get a closer look at defects like this AI image here, that would be considered an advanced assessment. And pictures or videos of defects are commonly taken to better inform the tree risk assessor. And this is an alternative to putting a climber up in the tree, so it's generally safer. This is also generally more efficient, but there are some barriers to entry, at least in the US, where you have to obtain a pilot's license and some additional insurance requirements there for commercial use of drones. So that's something to be aware of if you're interested in using a drone for advanced assessments. Decay testing, of course, is a very common practice where decay is suspected. Here we've got a resistance drill, which is an invasive test to measure the relative soundness of wood at these drill locations. On the right, that's the results of some of these drills. Another form of decay testing is sonic tomography, which is also fairly common here in the United States. This technology measures the time it takes sound to travel between sensors on a 2-dimensional plane of the tree's cross-section. You can combine multiple planes to get somewhat of a 3-dimensional representation of the internal soundness of the trunk. Here we've got an output of sonic tomography where the colors on this diagram indicate the relative speed of the sound waves, where blue indicates the slowest and brown indicates the fastest. So the brown areas indicate sound wood, while the blue indicates hollow, and those pink or green would be less sound or decayed wood. Root assessments are another pretty common advanced risk assessment technique here. Pneumatic excavation is often performed, so the risk assessor can inspect and evaluate potential decay or potential girdling roots. a resistance drill is sometimes included in a root assessment to quantify some of that information. Another root assessment technique is ground penetrating radar that's been around for maybe a decade, but is still emerging. This tool is shown on the left there, and the outputs are shown on the right. This technology can detect location, relative size, and depth of roots. The outputs on the top there, that's a top-down root detection map on the top left, and a root heat map on the top right. The bottom map is a root morphology map, and these can be helpful when potentially root loss needs to be evaluated non-invasively, and can help inform a risk assessor for potential whole tree failure. Load tests, these are not as common as some of the other techniques that I just discussed, and I'm not going to purport to be an expert on load tests, but I'm including it here because I know it is performed. And the objective of load tests are to assess the load required to initiate failure via uprooting or trunk failure. There's two different types. You've got static and dynamic. The static pull test diagram is shown here on the right, where sensors are installed on the root flare and lower trunk to measure the tree's response to simulated wind loads. And that's done by pulling the tree via a winch. These measurements are then compared to reference values to evaluate the load-bearing capacity of the subject tree. Dynamic load tests are similar, but use sensors that measure the movement of the tree over time during dynamic loading situations, which might include natural wind conditions. Lastly, we have stability analyses. This, I'm going to go briefly over Adbian that Ondrej and Simon will be talking about more in depth, but this analysis uses biomechanical principles and 3D LiDAR scanning to provide more data to the assessor, therefore more data to the tree manager. So you'd first collect your basic tree information, species, diameter, height. Then you take photographs of the tree. You collect full tree photographs and lower trunk photographs from different angles. This helps inform the wind load analysis of the tree crown. You'd then take a 3D LiDAR scan of the trunk, and these are input into the analysis. This can also be combined with resistance drilling, load tests, or tomography for more precise analyses. Here's an example of a couple outputs of the analysis. On the left is the analysis of stem dimensions at every few inches from grade to the height of your scan. This can help determine the weakest point of the trunk based on its geometry and the crown size and volume. And on the right is an analysis of the stem at the height that a tomogram was taken. Finishing up here, I wanted to discuss briefly how SavATree has been using Adbian before I hand it over to Ondrej or back to Katarina. Our consulting group has used Adbian software as an advanced assessment technique, as I've just described, to help inform our tree risk assessments. So we take the Adbian reports that Ondrej and his team develop based on our data collection and inputs, and we contextualize that information and data into an ANSI A300 compliant advanced tree risk assessment report for the tree manager. And Adbian helps add objective data to a fairly subjective risk assessment process, giving us more information to consider during our risk analysis. And we then provide relevant information to the tree manager so they can ultimately make a more informed decision about managing the risk of their tree. And that's really what the goal of tree risk assessment is. So thanks, Ondrej, for having me, and thanks everybody for attending this morning.
Thank you for an amazing presentation. even though it was, as you mentioned yourself, focused on like the American market and audience. I believe that those insights are very interesting and beneficial for everyone joining us globally today. So amazing, thanks. For everyone joining us today, JP already mentioned several test devices, and we'll be talking about more tools today later on. So we were actually wondering and wanted to ask you, what kind of test devices do you use in your practice? Okay, yeah, so a lot of you using either sonic tomograph or resistance drilling. Quite a lot. Yeah, it's still changing. Give it a minute and I'm gonna publish the results to all of you. So yeah, thank you for sharing this with us. And now we can move to the second presentation. The second presenter is Ondrej Kolarik. He is the co-founder and CEO of Adbian. JP already mentioned Adbian, but basically it's a tool that helps with tree risk assessments and really giving you precise objective data. We are using gliders, 3D scanning, and as mentioned earlier, we are a company from Czech Republic that recently partially relocated to the States. Ondrej is going to share some more. It's yours.
Thank you, Kate, for the intro. Good morning or afternoon, everyone, depending on where are you based. I'm really excited to share this presentation for the first time from the US soil, or not from the first time, if I don't count my presentation last year in ISA conference. But yeah, today connecting from Brooklyn, New York, excited to be here. Thanks everyone for connecting. Just a quick heads up, I'm used to do this presentation as 1.5 hour training course. So I try to keep most of the important information in. So just a heads up, this might be pretty information dense. So let's get to it. I named my presentation the Digital Toolbox for Consulting Arborists. I will briefly touch on some of the tools JP was talking about, but mostly I would like to expand your scope of what could be used to help you with assessing your trees. So I will be sharing a couple of apps. Some of them are free to download. So I will share directly the links for that. So it should be very practical. But first, I would definitely like to evaluate these tools together of how useful they can be for consulting arborists. So as a reference, I used a study from ISA and Tree Fund of most interesting research areas based on talking with the industry. So these were the most interesting topics based on the pool. So I chose the one that are connected to arboriculture consultancy, plus we will be talking definitely about technologies. So yeah, we will be evaluating these technologies based on these 5 metrics, plus I've added 2 extra. First of them, if this tool is accessible for everyone, meaning there is low barrier of entry, you don't have to buy any expensive hardware. And the second one, if the tool is scalable, meaning how much time it's going to take you to assess one tree, and we're going to make sure it's not like 30 minutes to hour per tree. So the technologies we will look into today are object measurements based on the pics, based on photos, photogrammetry, iPhone LiDAR scanning, AI, and lastly, advanced biomechanics, which is where we are using all 4 of these, and it kind of converges in one tool. As for the object measurements in practice, what I mean by this is that we are trying to recalculate an object size in a picture, and we have 2 approaches we can do that. The first one is if we have an object in the picture that we know the size. For example, the lady on the picture here is holding a pole that we know what the size is, and we can recalculate the rest of the tree based on the size of this object. Another way is trigonometry. So if we know the distance to the tree and we know the angle and the distance to the top of the tree, we can easily recalculate the height of the tree. But both of these approaches has a problem why these tools are usually not very precise, or these approaches, which is phone distortion or camera distortion. You can actually test it out yourself if you open your cameras and if you have the option to put 0.5 lens on, because there it's better visible. And if you just move with your phone around the room, you can see that the objects are getting bigger or smaller based on where they are on the display. This is called camera or lens distortion, and it tells us that the objects can really appear to have different size based on how the lens is distorted and where the object is on the display. And these can get pretty dramatic with the increasing distance to the objects we are trying to measure. How we are personally going about it is that we developed a phone calibration, which is a process of taking picture of this chessboard you can see here in different places of your phone, of your display, to recalculate what's the distortion of your specific device and how we can narrow it for the calculation of the objects of the trees you are trying to calculate. But for this specific task, I wanted to share with you an app called Arboriculture. And I have here a video from a park here in Brooklyn where I measured a tree with it. So you just come to the tree, you put the first point to the trunk of the tree. Then you move away from it so you can see the top. And then you select the base of the tree and the top of the tree. And it's going to give you the result. So this tree was 73 feet. It's here are the QR codes both for App Store or Google Play, depending on what device do you have. And I just gonna give you a few seconds to think about how this app specifically went about the phone calibration or about the distortion of the lens. If you remember, I told you that the distortion is the biggest at the edges, and in the middle, usually the distortion is the lowest. So they very cleverly put the central or use the central of the screen for the measurement of both the trunk, the base, and the top of the tree. And this is like clever way how to avoid the problems with the camera distortion. If we evaluate it based on our metrics, it doesn't really help us with most of the things we want to do with tree risk assessment. It doesn't much help us with communication or tree preservation, but it's definitely accessible for everyone, and it time to collect the data is less than 1 minute per tree. So we're going to move to our second technology, which is photogrammetry. Photogrammetry is recreating objects, 3D objects, based on 2D photos. So again, we're going to be working with photos, and these should be overlapping photos. Usually the best practice is around 75% of the photos should be overlapping with each other. And I have here again video of collecting the data. You might not hear the clicking sound of the photos, but you can see here it's loading pictures every several times per second. And I ended up doing around 50 pics on this tree trunk. And here you can see the result. So as you can see, this is super nice and super good communication tool for sure. The only problem with photogrammetry is with the measurements, that the objects are not up to scale. So it's nice representation, but you cannot really use it for any calculations. So as you can see, the app Polycam gives you a possibility to rescale. So you can input the real diameter or dBH of the trunk, but still I would be very cautious in using this in any calculations. Here are the QR codes for downloading the app if you are interested. Again, it's free. It has some free premium features, but I think the photogrammetry is free without any restrictions. What is good about photogrammetry is you don't even need to use your smartphone. You can use drones. You can use normal camera. So yeah, it's super. I would say it's super accessible. It's definitely a great communication tool if you want to show the tree owner what's the problem with the tree. But it doesn't really improve tree risk assessment because, as I said, these are not measured, so it cannot help us to preserve mature trees. Doesn't really push forward the tree sciences such as biomechanics. But since we have the pictures, if connected to the right tool, potentially it could help us with disease detection in the future. It's definitely accessible for everyone, probably the most accessible tool, and time to collect the data could be around 5 minutes, even with the data post-processing. If we move further to our next tool, which is LiDAR-based 3D scanning, JP touched on this a little bit, but the difference is the LiDAR is a specialized sensor that is shooting the beam, the laser beam, and it measures the time to reflect from the nearest object. So this technology has various use cases. It's used anywhere from self-driving cars to GIS solutions and stuff like that. The best part about this is really measures the objects. We are trying to stay accessible and scalable, so we're not going to speak about the designated LiDAR sensors, but again, you can buy today smartphones with LiDAR sensors included. Unfortunately, right now, it's only iPhones Pro, so no other phone manufacturer implemented these, but you can get LiDAR sensors anywhere from iPhone 12 Pro above. So it's a reasonably accessible investment. Again, I'm going to show you a video of the tree, how the data is collected. So you just come to the tree and start loading the data into your phone. So you are trying to get rid of these colorful or red squares. So yeah, you just walk around the tree, process the data, and here is the result. So even though it might look pretty similar to photogrammetry and it uses some practices of it, as I said, the nicest thing about it, it's actually measured and you can use these data for future calculations. So as I said, this one is only for iPhones. So if you have iPhone, feel free to scan this QR code. The app is completely free, so you can use it to scan with no restrictions. But let's stop with the LiDAR scanning in general and check how precise it can actually get. Because if we are using it for measuring, let's make sure it really checks out. So there, I chose 2 studies to assess this. First of them is from Stefan Rust and Lothar Göcke from Germany, where they measured or tested the placement of the sensors of a prototype for sonic tomography. So they scanned these sensors and then measured the distances and compared it to reality. And then they find out that the error rate was between 0 to 2%. So I would argue LiDAR scanning can be way more precise than even traditional measurements such as tape measurement because of the small error rate. I have here one more study, which is comparing the big LiDARs, the photogrammetry and the iPad and iPhone scanning, which has iPad and iPhone the same sensor right now. And even though if we account for poor lighting conditions and challenges with smaller trees with small diameter, the error rate was usually between 1 to 1.4 inches. So checks out pretty nicely with the 2% error rate from the previous study. So yeah, I would say this is the best tool for measuring tree trunks right now. But since so many of you selected that you are using sonic tomography as well, let's talk for a bit of how precise the sonic tomography is in this regard. There are not many studies on this, but I found one from Poland where they were comparing the tomographies with the real geometry of the trunk and the defect. And the accuracy of the damaged area was 90%. So inside it was actually, I would say, pretty good. 10% error rate, not great, not terrible, right? But the accuracy of the area plus damage was only 83%. So 17% error rate. So if you compare that with 2% error rate from radar, you will realize that tomography is not particularly good of getting the geometry of the cross-section right. But actually, if we gonna move to tree biomechanics, the cross-section and geometry of the cross-section is very important. I have here displayed a relationship between area of a cross-section and section modulus, which is a variable that is describing the geometry of the cross-section and its effect on the tree stability. I have here two examples of the cross-sections, right now simplified for a circle. First of them, even though it has smaller diameter, it has more wood, so bigger area of the healthy wood. And the second one has a smaller area, but it's spread it to a bigger diameter of the tree. So if we compare these two, they have actually the same section modulus. So we would say same effect on the stability, even though this one has significantly lower area of the healthy wood. The importance of the wood or of the healthy wood grows in tree biomechanics further it is from the center, right? So it's very important to keep this in mind. And also most of the tools are simplifying the geometry of the trunk for a circle or ellipse, but trees are rarely this simple if we are talking about bigger trees, because trees are complicated structures and their complexity grows with age. So we can actually use this LiDAR scanning to get closer to the reality and to get our models closer to what the tree really looks like and calculate on that. I have here a quick case study on this lime tree where the crown was selected for the wind loading. And then we compared four different approaches. First, we get the same area, and you can see the cross section on the picture below here. And we took the same area and put it on a circle, calculated the safety factor, and calculated the section modulus, which describes the geometry. We did the same for this cross section as how would tomography do that. So we placed 12 sensors and calculate the geometry. Then we did the real geometry, and then we did the real geometry with theoretical cavity here in yellow. So this one's just theoretical for the sake of calculation. And when we compare these approaches, the real geometry, which is this one, had 2.6 safety factor. Circle overestimated the safety factor by 38%. Tomography, so just between this and this, even though they look pretty similar, the difference was 23%. And the large cavity, which is the last one, subtracted from the stability 31%. Which means just a little bit of wood here and there on the edges can have similar effect on the stability calculation as pretty serious cavity on the inside. So if we want to really assess the complexity of the stability of the tree, we need both inside and outside pretty precisely. So I have here another case study in what we did with our tool, which is on the left cross-section of the tomogram, on the right the 3D scan in the same height. As you can see, they are not very nicely overlapping. And in this case, we've added 18% of healthy wood to the calculation. But since the outside wood is so much more important, it improved the stability by 39% of the overall calculation. We did more than, I would say by now, more than 10,000 trees comparing the real geometry and tomography. And if we learned one thing is that if you, on a simpler trees, they are aligning quite nicely. And as you are going to more complex trees, they are drifting further and further apart. And if you get to trees like these, you wouldn't even guess that the tomography was taken in the same height or on the same tree. This is from one of our customers in Ireland. So thanks, Drew, if you are watching for the case study. So yeah, if we evaluate this technology, LiDAR scanning can definitely help us with communication. It can actually improve the tree risk assessment because it measures. By itself, it's probably not going to help us to prevent tree cutting if we don't connect it with the calculation part. But it helps us to push forward the tree science, tree biomechanics, and it's definitely accessible for everyone. The barrier of entry is around $800 for the phone with LiDAR scanner, and the time to collect the data is only 1 minute. I have here one more tool or two more tools, so we're going to go super quickly through them. Another one is Luma AI, which is app to remodel the whole tree using AI and photogrammetry principles. It looks super cool, probably the most visual of the tools I'm talking about today. And the input of the data is literally just video. So you just walk around the tree. We're not going to play the whole of it, but you just walk around the tree and collect the video. And this is the result after post-processing. So as I say, it's super visual, super nice, but it has same problems as photogrammetry, because if you extract the point cloud itself, it's pretty bad and it's not up to scale for sure. So, but just wanted to put it out there because it's super accessible. It's on both Androids and iPhones, so you can scan your QR codes. And we get to the last technology, which is Adbian, our app we are developing. Adbian is short for Advanced Biomechanical Analysis. You can think of it as an advanced tool for data collection. You can think of it as device test without any expensive hardware. And you can also think of it as JP outlined as a tool to enhance your know-how with a technology, definitely not replacing the consultant in any mean. And what we see is that definitely with combination with resistance drills and tomographies, it can help us reduce unnecessary adult tree cutting. As JP was talking about the principle, so we are calculating with 5 photographies, 2 photos of the whole tree, 3 photos of the stem. The process of data collection is just you select the tree, fill in some details, and collect the photos. With each photo, we need to see the direction from which you collected it. If you check out the line, the phone has to be straight while taking the photo, and then you just measure the distance with each photo between you and the tree. So here is one example of 5 photos with the distances. Example of a report where we calculate the safety factor, which in general you would want above 150%. So if it is by itself, we display in the report that the tree doesn't require any stabilization pruning on the biomechanical calculations. But in the report, we are always calculating also a scenario how pruning would help you to improve the stability of the tree. We are selecting the crown for the wind loading analysis, which we are using to calculate the sail. And the wind speed for wind speeds, we are using the weather data and specific location of the tree. In the reports, we are also calculating what we call theoretical residual wall, because if you are not using resistography or tomogram, the tree is always calculated as a solid wood, which is often not the case. For example, if you are using Melot to validate this. So we are calculating always 3 scenarios, 30, 20, and 10% of the residual wall of the tree. You can see that this specific tree would be somewhat okay also with just 30% of the residual wall, but in general you would want safety factor above 150%. And last page are the pruning scenarios for different size of the pruning and how much it will improve the stability. So you can see you can get in the third scenario to doubling the stability if necessary. Stability pruning can be a great tool, but it cannot be overused because you are reducing the vitality of the tree by overpruning it. So here are the QR codes for our app on both Google Play and App Store. But as I said, for 3D scanning, you need an iPhone. And if hopefully it checks all of the boxes we want it to. I also have here comparison of all of these technologies together. And just wanted to close my presentation with the thoughts that definitely these technologies enables to do more and to do our work better and faster. So I would like to encourage you, try them out. Most of them are for free. You can just play with them because as you can see, the landscape of everything we do, not only in arboriculture, is quickly changing. So we don't know what the arboriculture is going to look like in 10 and 20 years. But the best way to stay connected to it, to stay connected to the progress is, and to predict the future is to partially create it. So use these tools and let me know if this was helpful for you. If you wanted to connect with me, here is a QR code for my LinkedIn. Also, as Kate said, we will be traveling the States. So if you would be interested in more hands-on training or testing out our solution, you can just schedule a call with me. I know I'm a little bit over time, so thanks everyone for your attention, and back to you, Katerina.
Yeah, perfect. No worries. Thank you very much. Great presentation. It's, I think, very interesting to see all those digital tools that can actually help the daily practice. Now, I think you are all, or I hope you are all doing fine, and you are ready for the last presentation we have for today by Simon. Simon Stratford of Stratford Trees is an ISA certified arborist with more than 25 years of experience. He used to do his work back in the UK, France, and now for a long time in the United States. We welcome Simon, who actually implemented some of the tools Ondrej just spoke about, and he's going to share his experience and maybe some case studies and practice.
Thank you very much, Katerina. Let's make sure I get this right. So as Katerina said, I started in the UK actually almost 28 years ago now, which is why I'm wrinkly and need glasses, and moved between France and Asia. And then we set up about 13 years ago in Florida. So I brought the sonic tomography with me. I want to show you how we have approached our client base, which is predominantly urban homeowners, and how I look at trees. So very briefly, risk. I see we've got a lot of people on here, over 150. Every single one of those people has a different view or appetite for risk, depending on your exposure, how you've been brought up. So it's very difficult to try and put things into one small envelope. When I arrived, my father-in-law, who has now passed away, was involved, one of the pioneers in the Gemini spaceflight program, and then on to the Apollo. And he gave me the guided tour, and the Saturn V rocket was inside. And he explained to me that there were 5 million parts involved in that rocket. And there was a 1% accepted failure rate, which seems small, but that's actually 5,000 parts. So risk is a very quantitative thing, depending on who you are and what you're involved in. The reason that Ondrej and myself got to know each other really was through the sonic tomography. And what I saw was a heads up on LinkedIn, and it was something to do with putting an overlay over the sonic tomography to give us a better understanding of the woody exterior of the tree. So that piqued my interest. And as Ondrej has very well described, that then led on to me using it and overlaying it, which gives us that extra wood. So this opening picture was unfortunately of a job last year, and you can see the big arrow, the failure point, the small arrow where we reduced that back, you can see unfortunately the guy's car underneath. So big word at the top. I was actually told my first ISA lecture I attended, and I asked about it, I was told that they don't use big words like that. So what is thigmomorphogenesis? And it's the changing shape of a plant, so we're talking about trees, in response to touch being light and wind. And you'll see as we go through that the recommendations for reduction are very tentative, and the bigger stability you get with a bigger reduction, but also you lose that movement in the canopy, which is critical in creating biomass response in the tree. So when I'm analysing trees, I'm looking for, it's hard with the younger trees, but the older trees, I'm looking for the biomass lay down, the twist and torque through the system to try and tell me what this tree is going through, how it's moving, because no tree grows anything with the express intention of falling over. It grows it with the intention of capturing light and staying upright to be able to do that. And so therefore, when we're looking at trees and trying to assess them, it's a bit like going to your doctor. He's going to ask you lots of questions to try and figure out what's wrong with you. We can't ask the tree, therefore we have to look at the signs. And there's probably an argument where you not only have to be an arboriculturalist, but you've got to have a good understanding of agronomy and biology. And there is a consequence to pruning because you are changing naturally what the tree has put down. There's a word there called protein denaturation and then climate underneath it, because climate changes have been going on through the last 5 extinction events. Ours is no different. I'm not saying we're about to become extinct, but climate changes, and whilst we were in Florida, it was reclassified from 9B to 10A. So the evenings are not as cool as they used to be. That changes soil, and when soil changes, whatever's growing out of it changes as well. And protein denaturation really is the breaking down of the three-dimensional structure of proteins, making them inactive, and it disrupts the cellular metabolism. So you get failure in tissue, and that is brought on by external stress, heat, drought, salinity, which is a big thing down there when we get hurricanes coming through. So there's a lot involved in it. We'll start going through. So I put this up very quickly this morning. Actually, my wife inserted it for me, but I saw it last night. And pH of soils will always tend to go towards acidity, just because of the potential of the hydrogen atom. And you can see that there are certain microbes, pathogenic bacteria, and fungi that are more active towards soil acidity. So if we're getting more rain and we don't take care of soil biology, that then starts to have a bigger effect, and that affects our sonic tomographies. Now, when we do sonic tomography and we come to a client, the most common question is my tree healthy? Mostly, I will go for basal scans, and if we detect decay, we haven't just walked upon it in so far as a tree has just manifested itself that week and we happen to spot it. It has often been there a very, very long time. So that creates our baseline. And then we will go back a year later, we go through exactly the same scanning points because we want a comparison as to the speed or not of transmission or activity of this bacteria or fungi. So looking at this tree, I've got to say that's probably a pretty typical, unfortunate pruning regimen in some of the areas I've been in Florida. You can see it was topped out and you got a lot of reaction growth along the back. That's totally changed the dynamic of the tree, and you see a structure underneath it. The failure direction is away from the house but could take the side of the building. So we've actually been scanning this for quite a few years. I've shown on here 2024 and 2025 to highlight the fact that there are changes which we are monitoring. Now, you can see the breakdown of walls. So I'm now going to go on to putting the loading analysis over the top of it. So you notice straight away it says that no stabilization pruning is required. So it generally has a safety factor over 150%, which is great. And then below that, you've got the two sonic tomographies levels and the stages of decomposition. So let me go to the next one. So you're showing direction and you can see the tree and the outline shape of the canopy. You might notice that the wind speed here that's been applied is 107 mile per hour, which is the top end of Hurricane 1 scale. So we do get windy down there. But it's a great analysis because when we're asked to go to clients' properties to look at trees, one of the things they always ask us is my tree healthy? So you've got physiological health and you've got structural health. So we're looking at structural health because physiologically it could be working fine, but it's no good if it's on the ground. In the beam model here, you will see that the weakest point is actually 6.6 feet from the ground, and the scan was taken at 1.1 feet. So the actual point of highest leverage or pressure exerted by that canopy is at 6.6 feet. So really what I'm looking for is how secure are the root flares? How good are they? And by using this tool and overlaying it with the 3D, we capture every single piece of extra wood, because to get a good sound transmission with the tomography, you're putting nails in place to get a good transmission, and that doesn't always mean that you're shooting through the root flares. You will see here at 1.1 feet. So a full profile, if there was no decay, going all the way through to if every single coloured part was theoretically not structurally viable, is still showing a good safety factor. And there's your stabilization pruning regime, and you will see going down to a 32% reduction, which is probably maximum amount of green material you want to take off. You increase it considerably, but not much by taking off just 10 to 11%. Once you start doing big pruning reductions, you're cutting across big cross sections of wood. So you're inducing early decay, and then you start having to think about, is this really a veteranization of the tree, and is a significant enough tree to keep and do that too? So there's a lot of consideration before you start messing around with the canopy of a tree. So this is an interesting one. It's a laurel oak. So there was generally a fault at the crown commencement canopy point. And you can see on the right-hand side toward the house, it's had some material removed. Its footer on the left-hand side hasn't really been touched. So he wanted to know whether the tree was safe, secure. So we did a scan at 210 centimeters above ground and then a little bit lower down. So that is just below that point of separation or where the crown commencement starts. Now you can see there is decay. I don't start right at the top because there is obviously a cavity. But the critical thing is, and I think JP showed it on one of his where you had a limb failure. In my experience, the attached wood, once you lose about 30% and the tree does its best to stop pathogen moving into the wood, it separates the material. And the leverage in the higher canopy then starts looking as though it will create a failure. We've gone down to 160 centimeters here. 210 centimeters is 6'11". So there's a reasonable amount, and it's a bit of a conundrum with this one, and we haven't made a final decision with the owner yet. You can see that it says there's a good stability with it, and even with the 2 levels of sonic tomography. But for me, it's a very large canopy. There's a lot of leverage on it. Now, there is another part of canopy dynamics that we look at as a company, and that's drag. And that's something that you can't replicate with load testing. Different types of drag, pressure drag, skin friction drag across the leaf surface. And then we look at the drag coefficient, air through it. And this is all altered depending on where the tree is, the width of the street or narrow, how it funnels wind, whether it's a single story or a double story building. How does that affect, and how has the tree grown into the roof shape to accept wind loading off of the roof? Because as soon as you start changing the shape of the tree, then you affect that. Now, the trick really with a tree, when it grows, and it has nothing to do with us, is disturbing airflow, drag, over the surface of the leaf by increasing the surface roughness. And that is why you get a lot of leaves, different shapes. Some have hairs on them, some don't, on the top surface. And the idea is that that roughness reduces the pressure drag and it increases frictional drag. And the overall result is that you get a reduction in drag. So that's what it does. So once you start reducing a tree and removing leafage, you are affecting its instinctive drag coefficient. If you think of a golf ball, it has lots of dimples all over it. And the reason it has that is to disrupt or disturb airflow. So this is something that, again, we've taken from nature to produce what we want in a recreational sport. So this is the canopy here. You can see a wind speed of 107 miles per hour. And interestingly, you can see it 7.5 feet. So that's only 6 inches above the point at which we scanned. It is showing that there is the greatest pressure point there. So this is a difficult one for us to decide what to do, because if you remember, taking a small amount off is not going to make much difference. But if you take a large amount off, we are changing the whole outline and how the tree behaves. But tools like this for us are imperative, because you need a lot of different ways to analyze trees and intuitively help you decide what this tree is trying to tell you and why it's grown. I mean, the safest tree is one on the ground, which is where I always start with a client. And they will say, well, no, I want to save the tree, but that's my baseline. So how do we make sure this stands up? And it's the smallest amount of work or change in the tree structure as possible to help it fit into its urban environment. And that's where the skill of pruning comes in. So there's different beam models. I'm going through to the sonic tomography analysis here, and you will see the safety factors still, if you remove everything that it's showing is possibly not structural material, you've still got a very good safety factor. So I've got to say, this is the thing that changed my mind. If I just used sonic tomography, I would have had a very different view on this 13 years ago, but not now. This here, it's a nice oak tree. Actually, it doesn't look too spectacular there, but it is. It's out on the river. There's he was worried about a lot of decay low down in the tree, and they'd let me show you. They put some decking around it and different things, and they were worried what they should put down to help it. This is what we showed as a sonic tomography. Solid wood, 44%. This is the statistics. Again, bigger pruning, we get a bigger safety factor, but essentially really no need to do it. I'm always interested in the 3D models, because a tree, as far as possible, left alone, will try to grow its canopy symmetrically. You can see from these views, that's exactly what it does. Directional photographs, these are better images, and you can probably see, let me just increase that. You can see there where it sits in this well, but it's actually a natural area underneath, so no big problem. And we can see that the actual highest pressure point and the weakest point that's been analysed using this is not at the base here, it's actually at the crown commencement canopy area, much, much higher. And there we go. If we remove everything that is showing, we've still got a safety factor of over 370%. Just a note on this theoretical residual wall, the thing that I love about this is that you can theoretically remove sound wood if you're not sure what's there. And you can position this on request at different heights in the tree if you spot something else that you're not too sure, some type of cavity. You can move that around, and that's a very useful tool for us. Again, there's the pruning regimen. So now I'm just moving on to some slides. This was last week up here in Montana. I was asked to go and look at some trees on a ranch around properties that are about 100 years old. They've been renovated. I spotted this, and little shout out to Amber Carson, who looks after some of our consulting work in Florida, whilst we're gallivanting up here and enjoying Wyoming, Montana temperatures. She's always close to the phone, and she loves fungi. So I said, okay, Amber, what do you reckon this is? So that sits at the base of this tree here, and you can see it's very unfortunate pruning, and they've removed material, so they've actually transferred weight to the highest point. The problem with that is if you want to increase the stability, you would naturally reduce, but you've lost the ability to do that because there's nothing to reduce it down to. There's no foliage. So it either stays or it goes. So we are doing a loading assessment on that, and we're going to do a sonic tomography through there. And then just down this way, you will see there's a tree very close to the house. And on one side, let me just highlight that a bit more. So an old lightning strike. There's quite a bit of decay inside. I have no idea what that looks like at the moment. So that's going to be a sonic tomography. I'm going to do it at 3 levels, so we create that 3D scan. I want to see what's happening up here and how much it's manifested itself down here, and what we got in the way of root flare. And we use the biomechanics on that as well. I want to know how much pressure is being created by this type of canopy, which looks as though it has been altered in the past. Once you start taking off, once you touch and prune a tree, you are removing apical growth. You are getting reactionary growth, which behaves entirely differently, is attached differently. The leaf structure is assembled at different places. Although it starts at the point of attachment, which is great when you've got a pollard, because that helps create the pollard knuckle and biomass. Gradually, with a lapsed pollard, as we call it, the leafage will move away from this area and it goes to the furthest point. And these do not attach themselves at the normal 45-ish degree angle. So you change the whole loading at the highest point, which is the worst place to change it. So once you start changing the shape of the tree, you've got to keep at it, because if you're doing it intuitively and you know what you're doing to achieve a certain result, then it's got to stay at that point, and the tree doesn't want to. It wants to replace what you've taken out. Thank you very much, and hopefully I'm back. I hope everyone understood that. That's the second part of the webinar in a foreign language.
Thank you for a great presentation again. Thank you all. We've got a couple of questions in the Q&A section, so I think we have still a couple of minutes to go through these. The first one actually popped up in the section while JP was presenting. With regards to the hollowing trees, how do you approach veteran tree management?
Yeah, I appreciate the question. It's fairly broad, I would say, and I could answer that in a very long period of time. But veteran tree management is, in the US, we don't have veteran trees per se. There's no standard way of classifying heritage trees, historic trees, etc. But generally, it would start, from our perspective, with a risk assessment, and it could go a bunch of different ways depending upon the situation and what's going on with that tree. But we take a good look at response growth to that decay to help us inform the vitality of that tree. Because if the historic or mature tree is not responding with response growth, then obviously that's a more vitality issue. If it has vigorous response growth, then that's not a vitality issue, and you're looking more at managing the risk. But yeah, I mean, I could go on and on, but I'll leave it at that for the other questions.
Thanks for the answer. Then we got another one that would be to Ondrej, I believe. Can you explain the metrics used to determine safety factors in this case and how that is quantified? Example, 150% of safety factor.
Yeah, that's also great questions. In general, in biomechanics, there is something called triangle of stability that tells us there is some load, in our case, wind load, or the weight of the crown of its own tree that is influencing the structure, the tree. And the tree can react either by its wood material properties or the geometry, how the material is composed. So for wind loading, we are actually using wind load based on, in US, based on building code, and in Europe, the same. So there is a building code, and the code is called ASCE, that tells you, based on the location in the US, how strong your house should be, to what wind speed. Yeah, so we are using this building code to apply for trees as well. So basically, if there is a storm in your area and it's not going to take your house, it shouldn't take your trees. So we are, working under this assumption for the wind loading. For wood material properties, we are assigning them based on several sources. We are working with Stuttgart table, but we are scouting other sources for different wood material properties. We were recently adding around 200 taxons for for North America. And for geometry, obviously, we are using the 3D scanning and photogrammetry data to remodel the real representation of the tree.
There was a similar question, more focused on the numbers itself, what the safety factor actually means. So there is the gray zone, and then you're in the green zone. Can you go more into details there?
Sure. So in general, and I saw a question on TRAQ there as well, so I will try to connect those two. In general, you would want your tree to be above 100%. But since biomechanics in general is acknowledging that, wood material properties or wind loading doesn't need to be precise, so we are not trying to say we are as close to the percentage. There is 50% buffer as a margin of error. So that's why you are trying to say above 150%, because we are acknowledging that biomechanics has its limitations, and in general as an industry. So that's why it's structured as it is. And as for comparison with TRAQ, question was, are there validated threshold or indicators from biomechanics data that could refine or challenge the current likelihood of failure component in TRAQ? I would just say the biomechanic has different scale for this. So it can be translated to TRAQ, but I would just try to look at it as a standalone data in your assessment. Or I don't know, JP, what's your opinion on this one? How are you actually combining it with the TRAQ scale?
I would agree with you. It's a separate data point that we are contextualizing into an industry standard tree risk assessment. So we're essentially judging the safety factor and helping that inform our likelihood of failure rating based on that. And I mean, safety factor is a common engineering term used to judge the strength of materials based on its expected loads. And so
failure points. Yeah.
we can maybe then spend some more time with a couple more questions, but I see people are actually dropping. So yeah, definitely they may have some other meetings. Then, as said, we can spend a couple more minutes with the questions for those of you who still have time and would like to keep the discussion. But for those of you who need to drop, again, thank you very much for being with us here today. Here is the list of the conferences that you can meet us in person here in the US or either New Zealand in October. And if you wish to go into more details, definitely feel free to book a free online call. We will be very happy to introduce everything and answer any of your other questions that you may have. There were also questions about the credits. So as mentioned at the beginning, if you are interested in the CEU credits, make sure you share your number with us so we can get that resolved and done afterwards. And also questions to the recording. The session was recorded and we will share the recording with you afterwards. So again, thank you very much. It was great having you. And as said, for those of you who still have some time, we can go through the questions, and those that we will not be able to answer today, I make notes, so we will try to answer those questions to your email directly, so you'll get the answers then. So thanks a lot.